After today's discussion, you will be able to understand the products of electrolysis, comprehend the Faraday's law of electrolysis, describe the conductance of electrolytic solutions, explain the measurement of molar conductivity and its variation with dilution, and the Colroche law of independent ions. In our previous discussions, we already discussed about the galvanic cell, which is one of the type of electrochemical cell. Now let us discuss the second type of electrochemical cell in which electrical energy from a source is supplied and it carries the redox reaction, which is otherwise non-spontaneous in nature. All these reactions basically involve the process of electrolysis. Electrolysis is the process of decomposition of an electrolyte when electric current is passed through either its aqueous solution or its molten state. The process of electrolysis is carried out in an electrolytic tank which is non-conducting in nature. We understand that electrolysis causes dissociation of the electrolyte into ions, which are directed towards the oppositely charged electrodes, where they either undergo oxidation by losing electrons at the anode or reduction by accepting electrons at the cathode. During this process of electrolysis, we get the products at the electrodes. These products depends on nature of electrolyte, concentration of electrolyte, nature of electrode, and the oxidizing and reducing species present in the cell. Let us now understand what would be the products of electrolysis of sodium chloride. We will take molten sodium chloride with an inert electrode of platinum. Molten sodium chloride is an ionic electrolyte which gives us the reaction as molten sodium chloride breaking into sodium ions and chloride ions. At anode, chloride ions undergo oxidation by losing 2 electrons, while at cathode, sodium gains 2 electrons and undergo reduction. Hence, sodium metal deposits at the cathode and chlorine gas evolves at the anode. We now consider aqueous sodium chloride with inert platinum electrode. Aqueous sodium chloride is a strong electrolyte and gets completely dissociated in aqueous solution. Water, which acts as a solvent here, is a weak electrolyte and is weakly dissociated. So, sodium chloride breaks into sodium ions and chloride ions. At the cathode, there is a competition between the reduction reactions. At cathode, sodium gains the electrons and the reduction potential is recorded as minus 2.71 volt, while the water gains the electrons and convert into hydrogen and OH negative ions. The reduction potential of water is recorded as minus 0.83 volt. If 2 cations are present in the electrolytic cell, the one which has higher reduction potential will get reduced first. Thus, hydrogen gas is evolved at the cathode while sodium ions remain in the solution because of its higher reduction potential. Similarly, at anode, there is a possibility of 2 oxidation reactions. The chloride ions undergo oxidation by losing the electrons, and the reduction potential is measured as 1.36 volt, while for the water it is measured as 1.23 volt. Since oxygen has lower reduction electrode potential, it was supposed to be released at the anode, but due to overpotential concept, chlorine gas is evolved at the anode while hydroxyl ions remain in the solution. What is overpotential? When feasible processes are kinetically slow, then extra potential is required to make the process happen, and this is called overpotential. The quantitative aspect of electrolysis was first described by an English scientist, Michael Faraday, during 1833 and 1834. The relation between the quantity of charge passed through an electrolyte and the amount of the substance deposited at the electrodes forms the basis of two important laws known as Faraday's laws of electrolysis. According to Faraday's first law of electrolysis, the mass of the substance deposited or liberated at any electrode is directly proportional to the quantity of charge passed. Let W be the mass of the substance produced at the electrode when a charge of Q is passed through the electrode. So, W is directly proportional to Q according to Faraday's first law of electrolysis. This can be also written as W directly proportional to I into T because charge is the product of current and time. And we may simplify it as W is equal to Z into I into T, where Z is the proportionality constant and is known as electrochemical equivalent. It can be defined as the mass of the substance deposited by passing 1 coulomb of charge or by passing 1 ampere of current for 1 second through the electrolyte. Its value is equal to equivalent weight divided by 96500 and it is denoted as E. According to Faraday's second law of electrolysis, when the same quantity of charge is passed through the solutions of different electrolytes connected in series, the masses of the substances deposited at respective electrodes are directly proportional to their equivalent masses. Let us understand this with an example where same quantity of charge is passed through aqueous solutions of copper sulfate and silver nitrate and are taken in two different cells in series. Copper and silver gets deposited at the cathode in both the cells and their masses are equivalent to their equivalent masses. According to the law, mass of copper deposited upon mass of silver deposited is equal to equivalent mass of copper upon equivalent mass of silver. This can be derived from Faraday's first law as W is equal to Z into Q, that is electrochemical equivalent into charge. For the first electrode, we may write it as W1 is equal to Z1 into Q1 or as E1 into Q1 upon 96500. For the second electrode, we may write it as W2 is equal to Z2 into Q2 or E2 into Q2 upon 96500. Since the same charge is passed through the system, Q1 is equal to Q2 is equal to Q, and so we get the expression as W1 upon W2 is equal to E1 upon E2. Before we proceed to understand the conducting nature of electrolytes, let us understand the significance of some basic terms involved. Conductance is the ease with which the current flows through the electrolyte. It is considered as the reciprocal of resistance of electrolyte and is denoted as G. G is equal to 1 upon R, where R is the resistance. It is also equal to 1 upon rho L by A, where rho is the resistivity, L is the length of the wire and A is the cross-sectional area of the wire. From our previous knowledge, we know resistance is directly proportional to length and indirectly proportional to cross-sectional area, and rho is the proportionality constant called resistivity. The quantity L by A is called cell constant and is denoted by the symbol G star. and 1 by rho is called specific conductance or conductivity and is denoted as kappa. G is equal to kappa upon G star or kappa is equal to G into G star. Hence, conductance can be defined as the property to conduct electricity in a cell with two electrodes of unit cross-sectional area separated by unit length. Thus, the units become ohm inverse, centimeter inverse. Ohm inverse can be written as Siemens, so the units can also be written as Siemens centimeter inverse. If we consider molar mass of the electrolyte, we may regard the conductivity of the electrolytic solution as molar conductivity. It is the conductance of all the ions produced by 1 gram mole of the electrolyte in solution and is denoted by lambda m. Lambda m is equal to kappa by C into 1000, where kappa is the conductivity and C is the concentration. It can also be written as kappa upon molarity into 1000, where molarity is denoted by capital M. The units then become ohm inverse, centimeter square, mole inverse. Both specific conductance or conductivity and molar conductivity change with concentration of the electrolyte. From the expressions discussed, we realize that conductivity of an electrolyte decreases with the decrease in concentration, both for weak and strong electrolytes. This is due to the fact that the number of ions per unit volume they carry, the current in a solution decreases on dilution, whereas molar conductivity increases with decrease in concentration. Conductivity depends on the number of ions and the mobility of these ions. Let us understand this with an activity. Let us take a beaker containing sodium chloride and connect it to a circuit which includes a LED bulb and a battery. As soon as the circuit gets complete, the bulb glows instantly. Let us now attach this circuit to a beaker containing acetic acid. What do you observe? The bulb glows with dim light. Let us start adding distilled water to this system slowly and gradually. What do you observe? The bulb starts to glow bright. The intensity of bulb increases as we add more water to the system. What do we infer? Sodium chloride is a strong electrolyte and conducts electricity readily. This is because strong electrolytes dissociate completely into its ions, and that is why the bulb glows bright. Acetic acid is a weak electrolyte which dissociates partially into its ions, and thus the bulb glows with dim light in the beginning. On adding the water, we enable the electrolyte to dissociate more, which increases the number of ions as well as the mobility of ions. This helps in conducting electricity and bulb glows gradually. This behavior can be well explained with the graph plotted for strong and weak electrolytes. The graph is plotted between the molar conductivity lambda m and concentration of the electrolyte C. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity. For a strong electrolyte, limiting molar conductivity lambda m naught can be determined by extrapolating the graph, as lambda m varies linearly. But for a weak electrolyte, the graph obtained is a curve, so it cannot be extrapolated to 0 concentration, and we cannot get the value of limiting molar conductivity lambda m naught for weak electrolytes. For this reason, we now need to understand the Colroche law of independent migration. Colroche law states that at infinite dilution, when the dissociation is complete, each ion of the electrolyte makes a definite contribution of its own towards the molar conductivity of the electrolyte and is quite independent of the presence of the other ion of its electrolyte. Thus, the molar conductivity of an electrolyte at infinite dilution is the sum of the ionic conductivities of the cations and anions multiplied with the number of ions present in one formula unit of that electrolyte. Lambda m naught is equal to nu positive lambda naught positive plus nu negative lambda naught negative. We can thus calculate the limiting molar conductivity of a weak electrolyte by using the limiting molar conductivity of strong electrolytes. For example, if we have the limiting molar conductivity of strong electrolytes like hydrochloric acid, sodium acetate and sodium chloride, we can calculate the limiting molar conductivity of a weak electrolyte like acetic acid. According to Colroche law, lambda m naught of acetic acid is equal to lambda naught of H plus lambda naught of acetate ions. Lambda m naught for hydrochloric acid is equal to lambda naught for hydrogen ions plus lambda naught for chloride ions. Lambda m naught for sodium acetate is equal to lambda naught for sodium ions plus lambda naught for acetate ions. And lambda m naught for sodium chloride is equal to lambda naught for sodium ions plus lambda naught for chloride ions. Thus, we may get the limiting molar conductivity of acetic acid by simply rearranging the values of the given data as lambda m naught of acetic acid is equal to lambda m naught for hydrochloric acid plus lambda m naught for sodium acetate minus lambda m naught for sodium chloride. Molar conductance of an electrolyte also depends upon its degree of dissociation. Alpha is the degree of dissociation which is equal to lambda m upon lambda m naught, where lambda m is the molar conductance at given concentration and lambda m naught is the molar conductance at zero concentration. This degree of dissociation can be used to calculate dissociation constant Ka, and so we may use the expression as Ka is equal to C alpha square upon 1 minus alpha, where alpha is the degree of dissociation and C is the concentration. To summarize the discussion, we may recapitulate that the electrolytic cell converts the electrical energy from a source into the chemical energy in the form of a redox reaction, which is otherwise non-spontaneous in nature. Such reactions take place in the form of electrolysis and follow the rule that if two cations are present in the electrolytic cell, the one which has higher reduction potential will get reduced first. During this process, the products of electrolysis are obtained at the electrodes. The process is justified with the explanation of conductivity of electrolyte, where the concentration of the electrolyte is taken as 1 molar and is referred to as molar conductivity. The molar conductivity varies with concentration for both strong and weak electrolytes. The limiting molar conductivity, which is also known as conductivity at infinite dilution, can be graphically obtained for strong electrolytes, but not for weak electrolytes. For weak electrolytes, we use the Colroche law, which help in calculating the limiting molar conductivity of weak electrolytes by correlating with the limiting molar conductivity of strong electrolytes. As an application of Colroche law, we may also calculate the degree of dissociation and acid dissociation constant for the electrolyte. Before we conclude, let me give you a numerical based on the concepts discussed in today's session. Calculate the limiting molar conductivity of ammonium hydroxide when limiting molar conductivities of ammonium chloride, sodium hydroxide and sodium chloride are respectively given. If the molar conductivity of a 0.01 molar solution of ammonium hydroxide is 9.33 ohm inverse centimeter square mole inverse, calculate the degree of dissociation alpha and dissociation constant Ka for ammonium hydroxide. I hope you have understood the concepts discussed in today's discussion. Have a nice day.